Okay, so picking up where we left off, this is the second video with your imaging digital characteristics. So here is your image quality characteristics. So we're talking about brightness, contrast resolution, and spatial resolution. So with your brightness resolution, it refers to the appearance of the image on a display monitor. So no technical adjustments during the image acquisition will change the brightness of the image. It is strictly a display quality. So it's important to know that it is a display quality. The technologist can adjust the brightness of the image by using the window level function. Then that'll change the brightness. So contrast resolution refers to the ability of the digital system to display subtle changes in shades of gray. So higher contrast resolution is the difference between adjacent densities are enhanced, so there's more shades of gray, and the ability to differentiate between small differences in densities. So contrast resolution in digital imaging is directly related to the bit depth of the pixels in the image. So remember how we talked about the 256, so that's your shades of gray. So dependent on the amount of, is also dependent on the amount of scatter. So collimation and the use of grids will allow for higher KVP without compromising the contrast resolution. So as you know, as the higher the KVP we go, the more scatter there is. So the grids are going to clean that up, allowing us to have more shades of gray. So with spatial resolution, the ability of the imaging system to demonstrate small details of an object. So the phosphor layer thickness and pixel size determines the resolution of the PSP system. So thinner the layer, the higher the resolution. So remember we talked about that. So digital imaging systems is about 2.5 line pairs per millimeter and up to 10 line pairs per millimeter in a PSP system. So the dynamic range of the image does not equate to higher spatial resolution. So more tissue densities are seen, giving it the appearance of more detail, but it does not. So smaller pixels give you the higher spatial resolution. So for example, an AP knee, this is film screen, so does not show the soft tissues like you normally would see on a digital system. So here is your digital system. You can see all the soft tissues, so it has a wider dynamic range, allowing for the tissue densities here that you can see with digital compared to in film. So this is due to a wider dynamic range. It does not mean that there's additional detail. The detail is the same, it's just giving you more shades of gray. All right, so your modulation transfer function, so your MTF, it's the ability of the system to record available spatial frequencies. So quantifies the contribution of each system components to the overall efficiency of the entire system. So the sum of the components in a recording system cannot be higher than the whole system. So when one component function is compromised, the whole system is compromised. Is a ratio of the image to the object, so that a perfect system would have an MTF of 1 or 100%. So an MTF of 1 is a perfect system, 100%. So in digital detectors, when an X-ray photon energy excites a phosphor or scintillation layer, the phosphor produces light. So the spreading out of the light will always occur. So light spread reduces the system's efficiency. So the more light spread, the lower the MTF. So as you can see here, we have 100%, so this is a 1. You see real dramatic here, and this is real small here. So noise. We've talked about noise in great detail, but noise is anything that interferes with the formation of the image. So radiographic noise occurs during the acquisition of the image. So equipment noise is caused by the detector elements or non-uniform detector responses. So the radiographer, we can't control this, and it's highly dependent on the manufacturer, the technology, and the detector quality. So it's out of your control. So quantum noise is a recording error in the digital image. So noise power spectrum, so the NPS, it describes the spatial frequency content of the noise as well as the spatial characteristics. So the higher the NPS, the higher the noise for a specific detector. So your signal to noise, your SNR, It's how much noise can be tolerated by the radiologist. As SNR increases, noise decreases, but exposure increases to the patient. So we deal with SNR a lot when we work in MRI. We are actually setting our SNR. So we can take our matrix and play with our matrix to get our SNR. We want a high SNR. It adds time, unlike in radiography where it's just going to, radiography will increase the patient dose, but in MRI it just adds time. So we do deal a lot with SNR as you go into advanced modalities. So here, this is just noise, okay? So this is low noise, this is high noise. You can see all the artifact on that image. Exposure latitude refers to the range of exposure values the image detector is able to produce. So values just above background noise are higher. So latitude depends on the image detector. So the higher the dynamic range of the detector, the more values can be detected. In addition to the range of exposures and the way the detector responds within a range, images have sufficient contrast resolution for the signal to be detected. So signal from an anatomical part must be appropriate to provide enough gray levels so it can be separated from background noise. So as you can see here, this is high contrast, so you can see the object and it's different from the background, whereas this is homogeneous, so it blends right in with the background, so you can't see the difference. Your defective quantum efficiency, so your DQE, describes how efficient a system converts the X-ray input signal into a useful output image. So the DQE is measurement of the percentage of X-rays that is absorbed when they hit the detector. Systems with a higher quantum efficiency can produce higher quality images at lower dose. So amorphous selenium, amorphous silicon, TFT, and charge coupled device, so your CCD, and complementary metal oxide semiconductor detectors technology have increased DQE over PSP. So your amorphous selenium detectors have the highest DQE because they do not have the light conversion step. So there's no light spread. So no light blur to the recorded signal output. Less dose is required than for others, and the higher quality images are produced, therefore. So newer CMOS capture systems may be equal to direct image acquisitions because of the crystal light tubes, which prevent the light spread. So in summary, there's two types of images existing in radiography. So there's analog and digital. Analog images are those that are made of continuous, varied levels of brightness and colors, whereas the analog captures of an image involves the measurement of continuously changing signal. Digital imaging captures represents a finite number of bits of information. For analog systems, X-ray energy is converted to light and recorded on film. In digital imaging system, multiple samples of the signal are taken. And digital images begin as analog signals, which are recorded and turned into electrical signals, which are then digitized. Digital images consist of pixels, which can be different sizes and shades of gray. The smaller the pixel, the greater the number of pixels can be used for an image, and the greater the depth and more shades of gray that can be recorded. So pixels are arranged in columns and rows called the matrix. The larger the matrix, the smaller the pixels. So as you know, the smaller the pixels, the higher resolution that we have. So that's your summary. So these two are your summary. Make sure you study up on that and you read your chapter so that you do well on your quiz.